Hey everyone, welcome back to Power Electronics. I'm Tim, and today we're going to be talking about isolated converters again. So, what I wanted to look at were buck-derived topologies. And just to remind you guys, where we kind of left off was here, right? So we came up with the idea of using transformers in DC converters by, having some DC source, converting that into an AC voltage, right? Which is kind of what switch mode power supplies do anyways, right? Considering the VX node, there's an AC component and a DC component, right? So we have some DC to AC converter, right? Followed by our transformer. And I'm going to draw this, non-ideal transformer, which has leakage and magnetizing. And then we follow that with an AC to DC converter, right? Because the transformer can really only transform AC voltages, right? And then our load follows that. So we produce a DC voltage from the AC provided by this transformer, right? And there's some dots, turns ratio, right? This is what we were looking at. So what I wanted to do today was kind of choose some blocks to go in these areas, right? So I wanted to talk about this, kind of have a few options, and here we kind of have a few options. And I want to talk about buck-derived isolated DC to DC converters because the conversion ratio is going to be pretty similar and it's going to be pretty easy to understand. There are other types of topologies, but we're going to start here. So first, let's look at this. I'll call this part 1 and I'll call this part 2. So first, we're going to look at the inverter side, right? The DC to AC side. So DC to AC, I'll just say inverter, even though inverter kind of already implies that. So what do we got? Well, there are a few options. The two options I want to look at right now are the following. So to convert a DC voltage into an AC voltage without a DC component, right? We can do it normally with a buck, right? It goes between 0 and VG, but we want to eliminate that DC component, right? So a reminder, for the buck, the AC voltage, or the alternating voltage that we produce, is at the VX node, right? We can think about the switching cycle. And the AC voltage looks like this, right? Goes from VG to 0. And, of course, there's some duty ratio, right? So we want to do something similar, but eliminate this DC component, right? The DC component here is dVG. So what we can do, some topologies we can use, is basically, and just to remind you, this comes from, it comes from this kind of topology, right? This thing. That's Vx, this is Vg, right? This produces this waveform. What we can do is actually just use another copy of this. We can create another copy, and then that would produce our negative voltage. I'll show you what I mean. So the first kind of AC converter we can produce, or the first kind of AC thing I want to talk about, DC to AC inverter, looks like this. So again, this is kind of just a redrawing of the conventional buck, the two switches of the buck, right? And we can imagine that VG is somewhere over here, connected to this leg, we might call it, right? So we have one leg, and then to produce our AC voltage, we just add another leg, right? And you might be thinking, well, that has to be a positive voltage, that has to be a positive voltage. How do we produce an AC voltage, right? How do we produce the negative voltage? And the trick really comes by looking at the difference between these two voltages, right? So we have the voltage from this leg and the voltage from the other leg, and the voltage we look at is the difference between them. So we want to look at plus minus, I'll call this Vx, right? This is the voltage we want to consider. And what does this Vx look like? I'll call it Vx prime. What does this Vx look like? Well, we have 4 switches. So 1, 2, 3, 4. So there are kind of multiple states you could choose, but here we're only going to consider 3 states. So what are these 3 states? And why do we need 3 states? Well, it'll make sense when I draw it out. So one state, I'll call it Q1, Q4 on, right? This is one state. Another state is Q2 and Q3 on. And then finally is a state we can choose is everything off. And these are the 3 states we're going to use. The question, why? Well, if you remember, back to the buck, we kind of got this 0 voltage when we turn on this switch. However, if we turn on one of these switches, it just pulls one of these nodes to ground. And if we want the full thing to be 0 volts, there are a few ways of doing it. We could pull everything to ground, we could pull everything to VG, or we could leave everything off. Right? Those are kind of our 3 options. This is the option I'm going to choose, but really, this is to produce 0 volts. Right? So this will produce our positive voltage. This will produce our negative voltage, and then we also need a 0 state, a state that produces 0 volts, and that's what we're going to choose everything off. There are other options. This is just what I'm going to show to demonstrate how this works. So these are the 3 states we have. And then what does this look like? What does the voltage we produce look like? Well, we can draw it out right here, right? And what we're going to need to do is ensure that there's an equal positive and negative portion, right? If there isn't, then there's going to be some DC offset, right? Think back to the buck. So if we think back to the buck, because this is like always positive, there's always going to be a positive DC component to it. However, if there's an equal positive to a negative portion, then we're going to have 0 DC offset, which means it's going to be a completely AC signal. We want a completely AC signal because we don't want to saturate the core of the inductor of the transformer, meaning we want it to be symmetric about the x-axis. So what does that mean? Well, we want to draw Vx. We want to draw Vx prime of t, right? This thing, right? And we're going to consider 2 switching cycles, right? And this is just for convenience to make the equations look nice. So we have 2 TS. That means somewhere over here we're going to have TS. And then this allows us to define the duty ratio in a way we're familiar with. So in the first portion of the switching cycle, we're going to provide a positive voltage, right? Meaning Q1 and Q4 are on. So Q1, Q4, right? These are going to conduct. So what does that look like? Well, if Q1 is on, then this top node is going to connect to VG, and if Q4 is on, then this bottom node is going to connect to, well, this is ground, right? So that means that Vx prime is going to be VG. Then we're going to turn everything off, right? So all 4 switches are not going to conduct anymore. I'm just gonna actually let's just go back. So again, Q1 and Q4 on means that we're going to have VG here. Then we're going to turn everything off. Again, there are multiple ways to have a 0 state for this converter. I'm just going to arbitrarily choose turning everything off. When everything turns off, well, basically everything is floating. And if all else being equal, these 2 nodes should be at an equal voltage. There's some division between the capacitances of the switches. We'll just assume that it will go to 0. You can guarantee it by turning on switches 3 and 4 or switches 1 and 2. Now, this is just an example. So this is what we get for the first half, right? The first switching cycle, right? So this we're going to control with the duty ratio. So this is going to be DTS. Say that here, DTS. And then we're going to do the same thing in the second half, right? Except here, for this first portion, right? Again, this is also going to be DTS. This length is going to be DTS. Q2 and Q3 are going to conduct. So when Q2 conducts, well, that connects the bottom node to VG, right? And the positive node is going to connect to ground, right? So basically we invert the voltage, right? It's an inverter. So we invert the voltage and we get negative VG here. And then again, we turn everything off to achieve a 0 state. So we have minus VG, that's on for DTS, and we have VG that's on for DTS. And all the other portions of time are 0. So this is the waveform we get, right? And it looks like the same as a buck converter, right? Except that we have equal positive and negative portions. So the equal positive and negative ensures 0 DC offset, which means we have a completely AC signal, which is exactly what we want for the transformer. So this is one option. This is known as a full bridge, right? This is a full bridge inverter, we could say, or an H bridge, because it looks like an H, right? Kind of looks like an H. So this is one option we could have for the DC to AC converter. Another common option looks like the following. So another option looks like this. So again, we have some VG, and we connect it again. So we still have this idea of using this buck kind of leg to produce an alternating voltage. But instead of using a secondary buck leg, all we do is have a capacitive divider, right? So we have C and C, they're the same capacitance. And again, we do the same thing. We look at the difference between these two nodes. So ideally, I'll call this Vx, I guess that doesn't really work. I'll call it Vx star. So all else being equal, the voltage Vg should divide equally between these two capacitances, right? It's a capacitive divider. That's kind of what we expect. In real life, it's a little bit more difficult, but because it's going to be loaded, it should work out okay. But what we expect is that we get Vg over 2 across this capacitor and Vg over 2 across this capacitor, right? So this node is always at Vg over 2. So we can imagine that this is always at Vg over 2. Now, this first stage, which we'll call switch 1 or Q1 and Q2, we're going to do something similar, right? So what we're going to do is, again, we have 3 states. So in one state, we're going to have Q1 on. In another state, we're going to have Q2 on, right? And then the third state, both off, right? And so this is going to be our 0 state again. And this is going to be our positive, and this is going to be our negative. So again, what does the waveform look like? When we do this, what kind of waveform do we get? So we're going to draw Vx of t. Again, we want it to be symmetric around the x-axis. We're going to consider 2 switching cycles to complete. So I'll call this Vx star of t. We're going to consider 2 switching cycles. So that means we have our 1 switching cycle here. Again, we consider DTS because we still want to pulse width modulate these converters, so we're using the duty ratio to control that. Here we're going to have Q1 on, so Q1 is going to conduct here, right? So if Q1 is on, then what does that mean? Q1 is on, then we connect this positive terminal to VG. So this is at VG, this is at VG over 2. The difference between these two voltages is VG over 2. Right, so that means we're going to have Vg over 2 here. So this half bridge inverter has half the gain. Right, that's kind of the trade-off. You have 2 fewer switches, but you have half the gain. Or really, the output voltage of this inverter is half. The amplitude is half that of the full bridge converter, full bridge inverter. So again, here we have Vg over 2. Then we turn both switches off. So if both these are off, none of these are conducting. Basically, the circuit becomes incomplete, and then the voltage should equalize. So this should go to Vg over 2. Again, it's a bit more complicated, but that is what happens. So it goes to 0. So if this node is at Vg over 2, then the difference between the positive and negative is 0 volts, which means we have 0 volts here. And then again, in the second switching cycle, the second half of the switching cycle, whatever you want to say, over here, again, this length is DTS. And here Q2 is going to conduct, right? So if Q2 conducts, then we bring this node to ground. This goes to 0 volts. The difference between the positive and negative is now negative Vg, right? or Vg over 2, negative Vg over 2, right? And again, we go back to the 0 state by turning everything off. And this is the waveform we get. So again, it's symmetric about the x-axis, meaning there is 0 DC component. And again, we can use this to send to a transformer and have an isolated converter, right? So we can use either one of these things. So this is like the first half. So this is one component we can use to construct a buck-derived isolated converter. Next, we want to look at the rectifiers. And again, there are a few options for this, right? So one rectifier option, again, we can imagine here for the rectifier. So we have the output of the secondary side of the transformer, right? You can imagine the secondary side of the transformer. One thing we can do is simply have a full bridge rectifier, right? An uncontrolled rectifier, basically. So 4 diodes, right? So what do? Well, we connect one terminal here, and we connect another terminal to the other side, right? And if we consider this voltage, I'll call it V secondary, and we follow this with basically a buck, right? So we have an inductor, a capacitor, and then our load, right? So again, this and this is our load. So this output side, this looks like the output of a buck, right? Right, so it's going to act like a buck, depending on whatever this voltage is, which I'll call Vx. It's going to take the average of Vx basically, and that is going to be your output voltage. So what is Vx going to be? Well, Vx is clearly going to be related to V secondary, right? And how is it related? Well, let's label these. So we'll have D1. We'll label the diodes D2, D3, D4, and we'll think about what happens when V secondary is positive and when it's negative. Coming back to the idea that this looks like a buck, what we can note is that V out is going to be less than whatever V secondary is, right? Because that's what a buck does, right? It steps down voltages. So if this is a buck, then V out is going to be less than V secondary, right? Let's just think about the magnitudes, the peaks of these voltages, right? So what does this mean? Well, we can kind of reimagine this whole section, right, this transformer section, as maybe being something like a voltage source that sits between these two terminals, right? And we'll call it V secondary. So V secondary is positive and larger than V out. Then what's going to happen? Well, again, we have an inductor here, and the current should flow in one direction. Let's say this is a load. Well, it's going to tend to forward bias D1 and D4. Why is that? Well, consider this. There's a voltage here, V out, which is smaller than V secondary, right? So if V out is smaller than V secondary, then the voltage drop will be positive across D1 and positive across D3, but it will be negative across D2 and D4. And D3, right? So if Vsec is positive, then Vsec then it will tend to forward bias D1 D1 and D4. Conversely, if Vsec is negative, it will forward bias D2 and D3, right? Meaning that Vx is going to look as follows, right? So we're trying to figure out what Vx is going to be. Well, what does a rectifier do? It makes both positive and negative voltages always positive, right? That's what a full bridge rectifier does. This is a full bridge rectifier. So if V secondary looks like this, again, we have these two switching cycles. And remember, this V secondary comes from the primary voltage, which looks like this, as we described before. And again, it could be VG or VG over 2, depending on which inverter we use. If this is V secondary, if we pass it through a rectifier, then it's going to make the negative portions positive and the positive portions positive, right? That's the whole point. So what we're going to get is that Vx of t, this is Ts, this is 2Ts, is going to look like this. Right? So this is either Vg or Vg over 2, whatever you want. And this looks exactly like, or sorry, NVG. I'll just call it Vsec. So we can say this is like Vsec and minus Vsec. This is also DTS. So again, this looks exactly like a buck converter waveform, except instead of VG, we have this voltage Vsec. So this is one option. This is one thing we can do. The second kind of rectifier that's pretty commonly used is something called a full wave rectifier, which is slightly different. Actually, one thing I didn't consider, or one thing I didn't say, is what happens when Vsec is 0. Well, that is actually the most interesting part, probably. So when Vsec is 0, then there's no difference between these two paths. And what will happen is that actually, depending on the different voltages, we could say that all 4 diodes conduct, right? If V secondary is 0, then all 4 diodes conduct, and then Vx goes to 0, right? The difference between this voltage and this voltage goes to 0 because basically there's a path to ground, so the current will loop in this direction, right? So when Vsec is 0, all diodes conduct, right? And actually what happens, like maybe ideally what happens, is that the inductor current splits evenly between these two branches, right? So maybe half IL will flow through D1, D3, and half IL will flow through D2, D4. IL over 2 through D1, D3, and IL over 2 through D2, D4, right? That is what tends to happen, right? So there's a kind of this special case when V secondary goes to 0, right? And that's kind of cool. So this is one rectifier we could have. Another rectifier is the full wave rectifier. And this is a little bit different because it actually modifies what our transformer looks like. In fact, it adds another winding. And a full wave rectifier is simply adding another winding with a center tap, right? So you can imagine you could stick a wire between the windings of a transformer. But the other way of thinking about it is that you just add a second winding, right? With the same turns ratio, right? Same dot directions. And what you do is you add diodes, right? That connect to the same node actually. Right, so they both connect up here. So this is like our positive node, similar for the buck, right? And this center tap is kind of like the ground node of our output, right? So again, we have L, we have C, and we have V out over here, and this is our load. So again, if we consider Vx, finding V out is simply looking at the average of Vx. So V out is the average of Vx. So what is Vx in this case? Well, again, we have to consider these voltages. So, what's going on? So we have Vsec and Vsec prime. So if Vsec is positive, I'll call this D1 and D2. If Vsec is positive, then what's going to happen? Well, D1 is going to be forward biased, right? And D2 will be reverse biased. And intuitively, you can think, right, we're applying a positive voltage to this side of the diode, which will tend to make current flow through the diode. Whereas for D2, we're going to have a negative voltage, right, applied to this side of the diode, which will tend to reverse bias it. If Vsec is negative, on the other hand, well, again, this is kind of Vsec prime. If it's negative, then D1 will be reverse biased, and D2 will be forward biased. And again, you can intuitively think like we're applying a positive voltage to this side of D2, which will tend to forward bias it. And then we're applying a negative voltage to this side of D1, which will reverse bias it. And finally, again, the question is, if Vsec is 0, then what's going to happen? Well, if Vsec is 0, then basically this is a short. This whole thing is a short, right? Because there's 0 volts across this winding, there's 0 volts across this winding, which puts D1 and D2 in parallel, and effectively splits the current between them. Right? So we kind of have three states again. One state D1 conducts, another state D2 conducts, and the third state, both of them conduct. And that kind of matches up with the way we're controlling the primary side, right? We have three states typically with the primary side. One state there's a positive voltage, one state there's a negative voltage, and one state there's a 0 voltage. So the 0 voltage state is really like very important to understanding how this works because it creates this synchronous rectification state that we have in the buck, right? Where we provide 0 volts to V out and allow control over the output voltage, right? The length of time that we have a positive voltage compared to the length of time that we have 0 voltage actually is what controls V out, right? If there was always a positive voltage at Vx, if it never went to 0, then V out could only be related to V secondary. But because there's like some period of time where it's on and some period of time where it's 0, then the average can be decreased and therefore controlled through pulse width modulation. So these are kind of our two options. So what happens if we stick these in, right? Right? We can freely kind of stick either inverter into the first slot and either rectifier into the second slot. So what happens? What do we do? So arbitrarily, I'm going to choose the full bridge rectifier on the primary side, and the full bridge inverter on the primary side, and the full wave rectifier on the secondary side. And what do we get? Well, we get this buck derived topology, a full bridge, you could say, so again, we have our positive and negative, which will connect to our transformer. And the positive and negative is very important because it's what allows us to, in a sense, relax the magnetizing inductance, right? We apply positive voltage, kind of charges up the core, and then we apply negative voltage, which relaxes the core, discharges the core, ensuring that our magnetizing current never goes above saturation, which ensures that we can couple the primary side to the secondary side. So we connect this to our transformer, right? So we have the non-ideal transformer with the magnetizing inductance. Which is then connected to, and here I'm going to choose 1 on the primary side and N on the secondary side, and because we're using a full wave rectifier, we have a center tapped core, right? So again, this is to N. So they have the same turns ratio, and we connect both of these to an inductor. So we have an inductor over here, followed by a cap, followed by our load, right? And again, we could choose either one for this. Full bridge, full wave rectifier, full bridge or half bridge inverter. But choosing this specific combination, this is what we get. So we have Q1, Q2, Q3, Q4, L leakage 1. And you could include a leakage on the secondary side. All right, so we could have L leakage 2, and we could have L leakage 3, and we have L magnetizing, and then we have finally our output inductor L, C, and V out is, over here. Maybe I'll just slide over a little bit. So V out is here, and there's with our load. And again, you can consider Vx here. And then this is kind of everything. So how does this work? Well, to understand how it works, we have to draw the waveforms. And there are a few waveforms to draw. So I'm going to ignore drawing like the leakage inductances for now, because really the magnetizing inductance is what matters most for this, and the output inductor. So again, we have 3 states. And the 3 states on the primary side align exactly with the 3 states on the secondary side. So 3 states. And the 3 states are Q1, Q4 are conducting on the primary side, and D1, right? So we're going to apply positive voltage here. So this is D1 and this is D2. D1 conducts. Then we have Q2, Q3 on the primary side conducting, and D2 conducts. And then finally, we have, you could say nothing, open circuit, or 0, whatever you want to say, nothing on the primary side, and D1 and D2 conduct. Right? That is how this thing works. So let's draw some waveforms. So what do we have? We have on the primary side. So I'm going to draw, how do we usually do this? Well, we draw the voltage across the inductors and then the current through the inductors. So first I'm going to draw V1, which is again the magnetizing inductance voltage. So this is going to inform us what the magnetizing current will be. So this is T, 2TS, TS. So again, we have our 3 states, and they're kind of 4 slots. So this is like state 1, state 2, state 3, state 2, right? So over here, we're going to apply Vg. Then it goes to 0, right? And when nothing's conducting. Then it goes to minus Vg. Then it goes back up to 0, right? So minus Vg, Vg. This is V1. And I should label what V1 is. So what do we have? This is V1, and then you could say this is V2. And you could say this is V3. They're related to each other because they have the same turns ratio. So that's V1. From this, we can draw the magnetizing current. So again, this is actually DTS, and this is also DTS. So the magnetizing current. So here, we're clearly charging up the inductor, which means we're ramping up with Vg over L mag, right? And we reach some peak current, whatever it is, and then here we discharge with the same amount. So this is minus Vg over L mag, right? And it goes back down to 0. So as long as this peak current is less than the saturation current, then we're good. So in a sense, this determines the minimum frequency we can have, right? If we switch too slow, then this current could get too high. So the size of the transformer kind of determines how fast you have to switch. The larger the transformer, the more core flux it can sustain, which means the slower you can switch, basically. And the smaller it is, well, the faster you're going to have to switch to ensure that it doesn't saturate. So this is a magnetizing current. Again, we have the primary voltage on one side, and now we can draw the secondary voltage. And the secondary voltage, or V2, is really just a reflection of the primary voltage, right? We have TS, 2TS, DTS, right? So in the first half, well, we apply VG, and we assume that we're coupling the primary to the secondary side. So V2 and V3 are going to be the same. So I'll just write that in as V2, V3. So it's going to look like V1 except multiplied by N, right? So V2 and V3 are going to look as follows. We're going to have NVG followed by 0, followed by minus NVG, followed by 0. Right? So we've stepped up the voltage, or we've transformed the voltage by our turns ratio N. Then this goes through the full wave rectifier, right? And again, as we described, it's going to force this positive and negative voltage to become fully positive. So if we draw the Vx voltage, it's going to look like this, but all the negative parts are going to be positive. So Vx is going to look like NVG, 0, NVG, and 0 again, right? And this is over 2 switching cycles. So this is why we chose 2TS instead of TS, just to make it so that at the output voltage looks nice. So this is, again, DTS, this is 2TS. Cool, so this is Vx, and we know that because this is a buck, the output looks like a buck. It's just an inductor and a capacitor. We could apply IVSB to L, but because we know that we're just averaging Vx, then we know that the output voltage, or really we can draw the okay, we'll draw the inductor voltage just to be fully complete. So this is T, this is going to be VL of T. This is 2TS, this is TS, DTS. So what is the voltage across the inductor? Well, pretty simply, it's going to be Vx minus Vout. Again, we're assuming that Vout is going to be constant. It's a constant voltage. We expect this to be a DC to DC converter. So simply, we just subtract off Vout. It's going to be some amount. I'll just draw it arbitrarily here. So we have NVG minus Vout over here, down to minus Vout. And then again, NVG minus Vout down to minus Vout. Right? So in a sense, we can think about the IVSB directly from this, but what I'll do now is draw the inductor current, IL of T. So we're doing the same thing we do with a buck. In the first half, we charge up the inductor, right? So there's some average current flowing through it, which is Vout over R load. Here we charge the inductor up with a slope of minus Vg over Vout over L. And then here we discharge it with a slope of minus Vout over L. And again, we charge it up again, and we discharge. Exact same thing. You have some average current. IL is equal to Vout over R load. And we could do the output voltage. The output voltage is going to look exactly like a buck. But really what I want to do now is think about what the average output voltage actually is. So Vout is going to be basically the average of Vx. And again, this is like a really simplified way of doing it, but we could do IVSB, so VL, the average of VL over one switching cycle is equal to 0. We can look at the VL over here. You can think about one switching cycle, so it's going to be D times NVG minus Vout plus D prime times minus Vout is equal to 0, which means Vout is going to be D times NVG, right? In other words, for this isolated buck derived topology, we get that the conversion ratio, M of D, is actually also a function of the turns ratio, and it's equal to N times D, right? So using this buck derived topology, we can actually step up the voltage by choosing a turns ratio that's larger than 1, right? So if, say, N is 100, then we can increase the input voltage by a factor of 100 and then step it down depending on our choice of D. Right? That is totally possible. So by using transformers, we can actually get buck converters to step up voltages, right? And sometimes that's useful. We can also get it to really step down voltages. So we could choose N to be really small, like 0.001, and we could turn a 100 volt input voltage down to like less than 1 volt. That's totally possible. And that's kind of the extra power, right? So this is like extra gain. We don't have to rely on duty ratio to control how big the voltage is at the output. Now we have this extra variable. Admittedly, you have to like decide what it is beforehand, but you can control it with N, right? You can choose, okay, I want the turns ratio to be 1,000 or 20 or whatever number you want. And again, we could fit in a half bridge on the input side. We could fit in a full bridge rectifier on the output side, and it would be a little bit different, but it would look pretty much the same, right? So if you use a half bridge, you just have to have a factor of 1/2 added to this because the input voltage is basically divided by 2. But other than that, it's pretty much the same. So that's it for now, just explaining the converter. Eventually we'll go in depth and like do a design thing with an isolated converter, but for now, that's it for this buck-derived topology. We'll talk about other types of isolated converters later. Thanks.